Greetings, chemistry students. Today we're going to start our overview of the periodic table. And this first slide, I'm just going to introduce to you a few names. I'll point out the ones you really need to know. But in 1864, a scientist named John Newlands came up with the first organizational scheme for the elements. Then in 1869, Dmitri Mendeleev and Lothar Meyer developed the first uh, periodic tables as we would recognize them today, and were able to predict unknown elements. And Dmitri Mendeleev gets most of the credit for this because only about 60 elements had been discovered when he was doing his work on the periodic table, and he was able to predict the properties of elements that had not yet been discovered. And so he gets more of the credit because he realized that he could actually predict things that we did not yet know. And his periodic table was organized by atomic mass because that was known about elements at the time. Then in 1913, Henry Moseley discovered the concept of atomic number. And so that changed a few things on the periodic table. Because if we look on the periodic table today, although it kind of appears that it's in order of atomic mass, it's not perfect. For instance, argon has a mass of 39.95, followed by potassium at 39.1. So there's some places where the atomic masses don't necessarily increase consistently like the atomic numbers do. So that's just one. That's just one example of where that happens. Or you have cobalt's 58.9, nickel's 58.69. So Henry Moseley, once he discovered the concept of atomic number, he figured out how many protons were in the nucleus. Then they were able to finally understand why the periodic table was arranged the way it was, even in the couple of instances where mass didn't quite seem right. And then in 1945, Glenn Seaborg placed the actinides in their current location. That's these elements down here on the periodic table. Most of those elements had not yet been discovered, but he was working on the Manhattan Project, and that's when they discovered some of these, like neptunium and plutonium and americium, and realized that they were a whole series of elements with very similar properties to each other that did not fit in with the rest of the periodic table. And the periodic law, by the way, the two scientists you should know from this list, you should know Dmitri Mendeleev helped develop the first periodic table, and Henry Moseley discovered atomic numbers and gave us the modern periodic table that we have now. The periodic law says that the physical and chemical properties of the elements are periodic functions of their atomic numbers. And the term periodic, it's a term that's used, for instance, to describe periodicals, which are magazines or newspapers that are delivered on a regular repeating schedule. It's also where we get the term for the female menstrual cycle that typically happens on a fairly regular repeating schedule. But this is saying that if you put the elements in order by atomic number, there is a regular repeating pattern that emerges. And so on the periodic table, we've arranged them to help clarify what some of these properties are. The periodic table has a couple of divisions. So we have the periods are the rows in the periodic table. And the properties change a lot as you go across each row, but each period follows a pattern. And there are 7 periods on the periodic table. 1, 2, 3, 4, 5, 6, and 7. And the pattern, you start with a very reactive metal, then a slightly less reactive metal, then some metals whose properties are kind of similar. Then you get to some elements that are kind of like metals, kind of not. Then you get to nonmetals. Then you get to very reactive nonmetals, and then you get to a gas that does nothing. And then you go to the next element is an extremely reactive metal, and the pattern just keeps repeating. Then you have families or groups, are the columns. There are 18 of them, 1 through 18. These elements down here are not in a group. And elements within the same family have very similar but not identical properties. So these elements over here are extremely reactive metals. These are extremely reactive nonmetals. Those are gases that don't do anything. So they're similar, but they're not identical. And so 4 of those groups have names that you should know. Group 1 is called the alkali metals. So that would be this group right here: lithium, sodium, potassium, rubidium, cesium, and francium. Group 2 is the alkaline earth metals. That's beryllium through radium. Group 17 is the halogens. That term literally means makes salt. And by the way, alkali means that it produces bases or basic substances, the opposite of acids. Halogen means makes salt. Chlorine, which is a major ingredient in table salt, is a halogen. And then group 18 is the noble gases, which, like members of royal families or nobility, tend to kind of keep to themselves and don't interact with these other elements on the periodic table. So those are some group names that you should know. So if I asked you to, for instance, name the noble gas in the third period, well, noble gases, this is your third period, that would be argon. There are some other divisions on the periodic table you should know as well. For instance, the representative elements or the main group elements are those in the S and P blocks of the periodic table. That's elements in groups 1 and 2 and 13 through 18. Because the periodic trends work really well, they're very visible and obvious with them. We'll get into what the periodic trends are tomorrow, but when we learn about the periodic trends, they work really well for those. Then there are transition elements or transition metals. These are the elements in the D block, and they don't have as much variation in their properties compared to the representative elements. So the transition elements are the ones in groups 3 through 12. On your periodic table, it also shows lanthanum and actinium as being transition metals. And then elements 58 through 71 are the lanthanides. This is a really original name. They come after lanthanum on the periodic table. And elements 90 through 103 are the actinides because they come after actinium. So these are the elements in the F region of the periodic table. And their properties are even more similar than the properties of the transition elements. These elements have very similar chemical properties. You might think, well, we don't use them. Sometimes they're called rare earth elements, which some of them are not particularly rare, and some of them have a lot of key uses. For instance, modern headphones rely heavily on neodymium in order for them to work. And then there is the staircase line on the periodic table, which this periodic table is missing it, but if I were to draw in the staircase line, it would be right here. And it just kind of stops right there. So this is your staircase line. It's on the one in your reference tables. And elements on the left side of the staircase line are metals. So all these elements over here, even these are considered on the left because really the periodic table is split right here between rows 3 and 4, and these elements are kind of in between there. So to the left of the staircase line are metals, except for hydrogen, which is kind of its own unique thing. For instance, there are some periodic tables that actually take hydrogen and just set it right here, where you just have hydrogen floating out in the middle all by itself. The properties of metals include luster or shininess, conductivity of both heat and electricity, ductility, meaning you can stretch them out into a wire, and malleability, meaning you can like hammer them out into flat sheets, kind of like aluminum foil. or they can take pieces of metal and stamp them to make the panels that they use to make cars and things like that. They also have low ionization energies, as we will learn soon enough, and lose electrons to form what are called cations. Not cations, but cations. So metals lose electrons. To the right of the line are the nonmetals. The nonmetals generally do not have luster. They are non-conductors. Instead of being ductile and malleable, they're typically brittle. They would have high ionization energies, and they would gain electrons to form anions. In other words, nonmetals are the opposite of metals. So your nonmetals are these elements over here. And then on the staircase line are the metalloids, except for aluminum. So your metalloids, I'm going to kind of identify them, are boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. So those are your metalloids. Their properties are kind of in between those of metals and nonmetals. They are semiconductors, and they're not good conductors or poor conductors, they're semiconductors. The one exception to this is aluminum. Aluminum is not a metalloid. Aluminum's just a metal. Okay, so aluminum fits in with all the other metals over here. Then hydrogen is its kind of own unique thing. So for instance, when we're talking about group 1 being the alkali metals, that starts with lithium. Hydrogen is not an alkali metal. Hydrogen sometimes behaves like a metal, sometimes behaves like a nonmetal, but it's also not a metalloid either. It's just weird.